We're going to close out our time spent with the gas laws talking about the combined gas law and give you an opportunity to use the combined gas law to solve problems similar to what you've done before. So as we review our three laws again, these should become pretty familiar to you by now. We have Boyle's law, which is an indirect proportion. Boyle's law is talking about a situation in which the pressure and the volume are changing while the temperature is constant. Talk about the fact that our temperature is constant here. And then when we talk about Charles' law, we're talking about the relationship between temperature and volume, and we have constant pressure. The pressure's not changing if we're talking about Charles' law in the truest sense. And then Gay-Lussac's law, in this situation, the volume is constant. Now, when we talk about Gay-Lussac's law, we're talking about a rigid container where the volume can't change, not a balloon, more like a tank of gas. Often, though, in real life situations, one of those three is not being held constant when we observe the changes in the others. One thing that we could talk about, and we could revisit the video that we saw that introduced us to Charles' law. In that video, they took a balloon and they put that balloon in the boiling water, and the first balloon that they used burst. Well, when we look at what was happening with that balloon, the balloon is going to change volume based on that temperature change, and this was all about Charles' law. We were looking at temperature and volume, but the pressure, what I want you to understand about the pressure on a balloon at any given time is there's this atmospheric pressure that's coming from the air around us, and so the atmospheric pressure is pushing on the balloon, and whatever gas is inside of that balloon, it's going to be pushing back. And when a balloon is not changing its shape, when it's just sitting there, the pressure on the inside of the balloon is equal to the pressure on the outside of the balloon. So what happens as we increase the temperature, that volume increases, and it increases until it gets to the point where the pressure is even again. The pressure is going to stay even all the time. What happens if we have a situation where the balloon can't increase in size anymore? Well, if the balloon stops increasing in size, now our volume isn't changing anymore, and then the pressure is going to go up. So right before that balloon bursts, the pressure inside that balloon started going up. And what happened was the volume of that balloon was increasing to the point that it was a strain on the material that the balloon was made of. The balloon couldn't stretch anymore. So at that point, you actually didn't have a equalization of that pressure. So when I was watching that video, I thought, oh, isn't the pressure going to change? At the end, the pressure is going to change. And it reminded me of the fact that all of these things sometimes change at the same time. But it's still an excellent way to look at our Charles law. But once that volume stops increasing in the balloon, then as the temperature goes up, your pressure is going to start to change. And that's the point I'm trying to make, is in real life, these things change together. In the when you look at your tires on an automobile in the winter, it gets cold, so the temperature goes down. The volume of our tire goes down, and we might look at it and say, "Oh, I need to add air to that tire because it looks flat, it looks lower." And of course, then the pressure gauge is going to show also that it's lower. So, all three of our entities that we're talking about, temperature, volume, and pressure, they change together. And that's why we have the combined law. And the combined gas law really just looks like the gas laws that we've been looking at combined together. We have the second temperature times the initial pressure times the initial volume equal to the first temperature times the final pressure times the final volume. So there's our variables. And if we look at that math relationship like we talked about last week, we know that it's the temperature that is directly proportional to the pressure and the volume. So if we wanted to talk about a constant being equal to our pieces here, we've got K is equal to P1 times V1 divided by T1. And then when we set that equal to the secondary situation, initial and the final, we would cross multiply and get our, we could cross multiply and end up with our formula. So what we have here is a really nice formula that doesn't have fractions that we can use to solve a problem in which all three things, the temperature, the pressure, and the volume, are changing. And that's what you're going to see in your work. So your first problem, if you've got your worksheet with you, as you read that, look for the pieces. Is there a second temperature? Is there an initial pressure? Is there an initial volume? Is there a final pressure? And don't forget, you need to make sure those temperatures are in Kelvin. So that's a pretty good place to start. Let's talk about our initial temperature. T1. And T1 is going to be 8 degrees plus 273 is equal to, I don't have a lot of space here, that's going to be 281 Kelvin. And then our second temperature, we have 84 degrees Celsius plus 273, and we're going to end up with 357 Kelvin. I'm going to squish that in there. And so always do that first. Get your temperatures into units of Kelvin. And then use your formula and start filling in the pieces. We have the second temperature. Well, my second temperature is 357. There's my second temperature. Kelvin, I'm going to put that in. My initial pressure is 362 kilopascals. And then we have my initial volume, which is 3.8 liters. And now on the other side of my equation, I've got my initial temperature, which is 281 kelvins. And I'm going to multiply that by my second pressure, which is 573 kilopascal. And then I'm going to multiply that by my volume. That's my second volume. That's my x. That's what I'm solving for. And so when we go to solve this then, what I'm looking for is I'm going to take these terms and I'm going to divide both sides of the equation by 281 and 5. I'm having issues here. 73 kilopascal. I'm going to erase that because I don't want to look at it. And make that work for me. There we go. I'm having issues with these tools here, and I don't know why, because I don't think I'm doing anything different. But so when I go to solve the problem, this is my x over here, volume 2. So I'm going to take 3. Oh, man. I am so not happy with this. I'm sorry, you guys. What is that, and how did it turn into that? All right, let me try this. I'm going to take my 357 Kelvin, and then I'm going to have my 362 kilopascal. I've got 3.8 liters. I'm kind of writing over that. It's a mess, I'm sorry. And then I'm going to divide by the two parts, the two terms from the other side of the equation that I want to get out of there, and that would be 281 Kelvin and 573 kilopascal. I hope you can follow this. And that's going to be equal to my second volume. So when you pick up your calculators, you're going to take 357 times 362 times 3.8, and then divide key 281, push the divide key again, 573, and that's going to give you your answer. Now my kickout number here is 3.04999. Now if I go back and look, I have 3 sig figs for my pressure, but only 2 sig figs in my volume. So if I'm going to round back to 2 sig figs, I'm really just going to call this 3.0 liters. Actually, when you go back then to your, if you really want to nitpick and call that 1 sig fig, then we just call it 3 liters. So be aware of your sig figs. We're not going to nitpick that with you, but it's such an important thing to think about when you do real research. We need to keep it in a part of our process. So your second example is a little bit different. It says a can of gas is at 30 kilopascals and 20 degrees Celsius, what is its pressure at 48 degrees Celsius? Now we start with the combined gas law, and I wanted you to look at this problem because in this situation, the can of gas is a can. It's not flexible. The volume is not changing. And the beauty of the combined gas law is you can always start with the combined gas law no matter which law is necessary, because in this situation, if the volume is constant, then I'm just not going to need to use the volume part of this formula. So really this is a temperature pressure problem, which makes this a Gay-Lussac problem. So I'm going to use my formula. What's my second temperature? Well, my second temperature is 48 degrees Celsius. And don't forget to convert that to Kelvin. Since I've got 3 sig figs here, I'm going to use the 273.15. If you didn't do that, it would be okay with me either way. My second temperature is 48 plus 273.15. So I'm going to call that 321.15. And that's in Kelvin units. My initial pressure is 30 kilopascal. Got my 3 sig figs there. And I'm going to set that equal to my initial temperature, which is 293.15 Kelvin. Where did I get that number? I don't see it in the problem. Well, I took my 20 and I added 273.15 and converted that to Kelvin. And then the problem is asking me for the pressure, which is P2. So you see, when we have the combined gas law, we can start with that no matter what the situation is. Every problem we've done since we've looked at Boyle's law and Charles' law, we could have started with this combined gas law. And then if one of those entities, one of those variables isn't changing, then that piece of it just goes away. It's the same on both sides of the equation, so it cancels out. So when you do the math, you're going to take 321.15 multiplied by 30, and then you're actually going to divide by the 293.15. We have 321.15 multiplied by 30. We're going to divide by 293.15. And our units of Kelvin are going to cancel. We're going to get units of kilopascal. And my kickout number was 32.86. I want to round to 3 significant figures. So that's going to be 32.9 kilopascal. For example number 2. So you have the problems on your worksheet. Here's just the first one I'm going to mention, and then we'll be done. You'll be able to do the rest of those without me because you're really following the same patterns that we've learned in the lesson about Charles' law and the Boyle's law. Here it says a gas takes up a volume of 17 liters and has a pressure of 2.3 atmospheres and a temperature of 299 Kelvin. If the temperature is raised to 350 Kelvin and the pressure drops to 1.5 atmospheres, what is the new volume? Well, the beauty of this one is they've given us the temperatures already in Kelvin. So what is the second temperature? We want to use 350 Kelvin. That's already there. What is the initial pressure? This time it's in atmospheres, but it's in atmospheres consistently, so we're good. Make sure the units of pressure are the same as each other. The initial volume is 17 liters. And then you're going to set that equal to the initial temperature, which is 299 Kelvin. And then our volume. That's our X. We want to know what the volume is. And so what I really don't like about how little room I have here to work with is that you're not seeing all of this in a row. So on both sides of the equation, you've got units of Kelvin and units of kilopascal, and so all of the units are going to cancel out until you have just the units of volume left. So you're going to solve for X, and then you're done. So you're going to go ahead and continue with the worksheet that you're using. The Edpuzzle will ask you some questions about those. I think that you're good to go. Always, always, always convert temperatures into Kelvin if they are not already in units of Kelvin. Make sure you convert that, and then make sure your other units are equal to each other. If the problem gives you a pressure in atmosphere, then other pressure should also be in atmosphere. I don't have any problems in this set where you're going to have to make those conversions other than converting to Kelvin temperature scale. There's nothing else tricky here for you. You're going to go ahead and use this formula each time. I do want you to be aware that if you have a situation where the temperature doesn't change, then you start with the combined gas law. If the temperature doesn't change, then it eliminates it. And look what you have. Once you block out the two temperatures, you've got Boyle's law. If you have a situation where the problem talks about pressure being the same, if it states that it's at constant pressure or the pressure doesn't change, then your pressure part of this formula just goes away. Eliminate it, and you are already dealing with Charles' law. It's a one formula fits all situation. And if the problem talks about a rigid container or having constant volume, then you're really dealing with Gay-Lussac's law. So the volumes eliminate, and you have the law. It's ready to go. So follow the instructions on your worksheet and complete your worksheet, and you'll have questions here for you about those.